Hi, I'm Norman Wildberger. Today we're going to look at some really beautiful theorems which I like to call the laws of proportion. So they concern a triangle, the usual setup A1, A2, A3, and its usual quadrants is Q1, Q2, and Q3, and the spreads S1 and S2 and S3. In addition to this triangle, we're going to look at one extra line emanating from A3 and intersecting the opposite side at some point. That extra line introduces some new quadrants and spreads. That quadrant's R1, that one R2, and that one R3, as well as these two spreads here, R1 and R2. And our aim is to establish this formula relating these various new spreads and quadrants. The only thing we're really going to use is the spread law. First we start with this triangle here and we use the spread law in it. S1 over R3 equals R1 over R1. Right there. And in this triangle here, the spread law, S2 over R3 equals R2 over capital R2. That's that one there. Now have a look at these two equations, 1 and 2. We're going to divide one of these equations by the other. So this divided by that is S1 over S2. And this right-hand side divided by that right-hand side is R1 over R2, capital R2 over R1. And I prefer to rewrite that by bringing the capital R's to the other side, so we get R1 over R2 equals S1 over S2, capital R1 divided by capital R2. That's the law of proportions for this triangle. And the way I like to remember it is to look at it like this. That ratio R1 over R2 equals that ratio there times that ratio there. Now if S1 and S2 can be replaced by the quadrants as Q1, Q2 from the spread law, then we could rewrite that also in terms of quadrants. There are three interesting special cases. Let's look at them individually. The first is when the triangle we start with is an isosceles triangle. We'll suppose that S1 equals S2. In that case, that constant there is 1, and we just get R1 over R2 equals capital R1 over R2. So the ratio between these two spreads equals the ratio between these two quadrants if the triangle is isosceles. The second interesting special case is when capital R1 equals capital R2. In other words, when this point here is the midpoint of A1, A2. In that case, R1 over R2 equals S1 over S2. The ratio between these two spreads is the ratio between these two spreads. And finally, if little r1 equals little r2, that's the case when this is a bisector of that vertex, then we have S1, S2 equals capital R2 over capital R1. Our next theorem is a famous theorem from antiquity, from 100 AD. It concerns a triangle A1, A2, A3 as before, and an extra line which now intersects the three sides in some random points. So we'll say that the intersections of this new line with the three original lines are B1, B3, and B2. And that the spreads made here are that one R1, that one R2, and that one R3. So those points give us a lot of new quadrants. And the labeling is quite consistent. So if you go cyclically around things, everything kind of matches up. So along this line here, for example, A1 to B2 is the new quadrant called P2, and that one's called R2. We also have a P3 here, and an R3 here, and a P1 from here to here, and an R1 from here to here. Alright, so now let's have a look at the spread law again in some various triangles. The first one is in this triangle right here. R2, that spread there, divided by R3, is capital R3 divided by capital P2. In this triangle here, R3, the spread there, divided by R1, equals capital R1 divided by P3. And finally, in this big triangle here, capital R1 little r1 divided by little r2 equals capital R2 divided by capital P1. That quadrant's there. Okay, so now we multiply these three equations together, and what happens? On the left-hand side, we have R1, R2, R3 divided by R1, R2, R3, which is 1. On the right-hand side, we end up with R1, R2, R3 divided by P1, P2, P3. So that's going to equal 1. That means that R1, R2, R3 equals P1, P2, P3. That's called Menelaus' theorem. And this formulation does not involve any signed distances. The usual formulation does. It's completely independent of actually where these points are with respect to the triangle. Okay, now let's have a look at the triangle A1, A2, 3 together with one additional point. And we've drawn some new lines, we've got some new quadrances, and the spreads labeled like this. Basically, it's the same story. We apply the spread law. So, for example, in this triangle, we have R2 divided by P3 equals N3 over N2. And then we play the same game for this triangle and this triangle. When we multiply these three equations together, then on the left-hand side, we have R2, R3, R1 divided by P2, P3, P1, P2. And on the right-hand side, the product of the three ends divided by the product of the three ends is 1. Which gives us the alternate spread theorem, namely that the product of the three P spreads is the product of the three R spreads. Now we take the same picture there and we extend those lines to meet the other side. We get new quadrances along the sides, R1, P1, R2, P2, and R3, P3. We're going to apply the law of proportions now to this triangle, to this picture, together with this line. What's it say? R1 over P1 equals this spread divided by that spread. In other words, S2 divided by S3 times R1 divided by P1. There it is right there. And then we do the same thing with that line and the same thing with that line. I'd like to check that those are the formulas. And then we, no surprise, we multiply them together. This times this times this equals the product of the R's divided by the product of the P's. But we've just decided from up here that that's equal to 1. So the product of the left-hand side is 1. The product of the ratios involving the S's is also 1. All what we're left with is the product of the capital R's divided by the capital P's, and that equals 1. So that means that the capital P's multiplied together equals the capital R's multiplied together. And this Sabus theorem allows us to solve the problem that we initiated in the last video with centroids. Because we can rewrite this in terms of the product of three ratios. We can write it as R1 over P1 times R2 over P2 times R3, that should be an R, R3 over P3 equals 1. So that tells us that if that's 1 to 1 and that's 1 to 1, then that's got to be 1 to 1 as well. Or say that's 1 to 1 and that's 1 to 2, then this has got to be 2 to 1. That's an R. Next time we're going to use what we've done so far to start thinking about circles. And it's going to be quite exciting. We're going to develop some nice theorems for them. I hope you'll join me. I'm Norm Wahlberger. Thanks for listening.